Hello all, in this video we'll learn about passive reinforcement learning. In the previous video we have seen what is reinforcement learning and I'll give the link for the video in the description below. Now we'll learn about what is passive reinforcement learning. Actually here the agent will be following a fixed policy where the policy is represented by pi. The passive learning attempts to evaluate the given policy pi without any knowledge of the reward function R of S and the transition model P of S dash given S comma A. We have already learnt about the reward function as well as the transition model. Now, this is usually done by any method of utility estimation. So now we'll see an example how the utility estimation is done. For example, consider a series of actions are given. Now to calculate the estimated utility U, we use the mathematical representation U pi of S is equal to expected average of gamma as well as the reward of S dash. Consider we have the given policy in this diagram. Already we have seen this scenario. We want to determine how good this policy is. So to determine how good this policy is, we will be calculating the estimated utility value U pi of S. So how to calculate the estimated utility value? We'll see. Actually, it is done by taking so many training epochs. Consider 1, 1 is the initial state. So from 1, 1, it can go to 2, 1, then from 2, 1 to 3, 1 and here, from here, if the agent moves here and then it moves back, then it goes to 3, 2, then 3, 3 and then 3, 4 where it is plus 1. So this movement is given in the first step. So similarly, so many training epochs will happen. So another kind of training epoch is, consider the initial status or the agent is until 1, 1. From here it moves to 2, 1 and then it goes to 3, 1. Then it moves to 3, 2. Then it moves to 3, 3. Then from 3, 3 it goes back to 2, 3 and then again it comes back to 3, 3 and then it moves to 3, 4. So this representation is given here in the second statement. Okay. Then the agent can also move in some other direction from 1, 1 to 1, 2, then 1, 3, then 2, 3 and 2, 4. In this case, it gets a reward minus 1. Okay. So similarly, so many training sequences will happen and whatever is the best will be taken or will be considered. Based on this concept, we have 3 methods for estimating the utility. The first method is direct utility estimation. The second one is adaptive dynamic programming and the third one is temporal difference learning. We'll see all these 3 methods one after another. So the first one is direct utility estimation. So here it estimates U pi of S as an average total reward of epochs containing S. It means that it calculates from S to end of the epoch. Then the reward. How the reward is calculated? The reward is calculated as the sum of the discounted rewards from the state until a terminal state is reached. And consider, we'll see this with an example. Consider the reward from the current state with an action. It moves to the next state will be minus 0.04 if it moves between the non-terminal states. So if this is the case, then how the utility is estimated, we'll see with an example. So for example, our agent is in position 1, 1. Consider our agent is in this position. Now from here it moves to 2, 1. Then from 2, 1 it moves to 3, 1. From 3, 1 it moves to again 2, 1. From 2, 1 again it moves to 3, 1. From 3, 1 it moves to 3, 2 and from 3, 2 it moves to 3, 3, and the agent moves from 3, 3 to 3, 4 where it reaches the goal state. Now we need to find what is the total reward. So how to find the total reward? When we have already seen R of S comma A comma S dash is equal to minus 0.04 for the transition between non-terminal states. So many transitions are made between the non-terminal states, and here only one is a terminal state, which is the last state or the goal state. So here, if there is a movement from 1, 1 to 2, 1, then the reward it will get is minus 0.04. Similarly, from 2, 1 to 3, 1, it gets the reward minus 0.04. Then from 3, 1 to 2, 1, again it is coming back, right? So for that it will be getting a reward minus 0.04. Now from 2, 1 to 3, 1. So here also it will get a minus 0.04. So likewise, till it reaches 3, 3, this cell, it receives minus 0.04 as reward. And now the agent moves from 3, 3 to 3, 4. So now it receives a reward plus 1. And then actually this is the path which is this is the path which the agent travels through. Now we need to add up all these rewards to get the total reward. Okay, so when we sum up all these rewards, we will be coming up or ending up with the reward value 0.72. So this value is said to be the observed reward to go for 1, 1. So from 1, 1, as of now, it has observed that to move to the goal state, it is getting a total reward value of 0.72. And for example, we will be considering another movement starting from 2, 1. It means that our agent is in this position 2, 1. From here, it takes one path to reach the goal plus 1. Okay. Now we will see that path, in which path it is moving on. From 2, 1 it is moving to 3, 1, and from 3, 1 it is coming back to 2, 1, and then from 2, 1 it is again moving to 3, 1, and from 3, 1 to 3, 2, and from 3, 2 to 3, 3, and from 3, 3 to it moves to another cell which is 3, 4, which is the goal node. Now we need to calculate the reward value, the total reward value. So when we calculate the total reward value, we get it as 0.76. Okay. Now from 2, 1 itself, another movement is also happening. That is, we will be doing so many epochs, right? So another epoch is happening from the same 2, 1 position. So now consider the agent is in 2, 1 position. So from here the agent moves to 3, 1, and from 3, 1 to 3, 2, from 3, 2 to 3, 3, and from 3, 3 to 3, 4. Okay, now it again reaches the positive goal. Now we need to calculate what is the total reward value. So what will be the total reward value? So we will be calculating here, and we are getting the total reward value as 0.84. So in this case, from the state 2, 1, we get two different total reward values, or the observed reward to go. We are getting two different values based on different paths. So similarly, we will be getting multiple path, and then we will be getting multiple values. So what we need to do is we need to take an average of it. In this case, we have two different paths and two different reward values. So we will be taking the average value. So it is, the average is 0.76 plus 0.84 divided by 2, which is equal to 0.8. So it means that from 2, 1 to reach the positive goal, the average total reward will be 0.8. So this is what we are finding out. And here the main problem is, it converges very, very slowly. Why? Because it is taking multiple steps, it is following multiple steps and it is finding the average. So the convergence will be very, very slow. So we go for the next method, which is an adaptive dynamic programming. So here it keeps track of how often you get to the state S dash given that you are in the state S and do an action A. So in this method, we will be using the knowledge of past state S and the action A, and whatever new state we are going S dash. All these things are used to estimate the transition probability P of S dash given S comma A. This ADP does this by the simple counting of new states resulting from previous states and the actions. Now consider an example. We are in the state 3, 1. From 3, 1, we can execute certain actions. One action is right as well as another action is down. From 3, 1, you can move to 3, 2. So when you do that, for example, while you doing this, twice the time you are moving to 3, 2 and one time you are moving to 2, 1. So now what is the transition probability? So the transition probability will be 2 by 3 because 2 times you are moving to the next stage 3, 2. Okay. So here we need to solve a system by simultaneous equations, and so it cost order of n power 3, and it is very hard to do if we have 10 power 50 states. It could make things a little easier with a modified policy iteration algorithm. The next one is temporal difference learning. Instead of explicitly building the transition model P, here in the temporal difference model, we make use of the expected closeness between the utilities of two consecutive states S and S dash. For example, for the transition from S to S dash, the update of the utility function can be written as u pi of x is equal to u pi of s plus alpha r of s, which is the reward value, gamma, then u pi of s dash, s dash is the next state, minus u pi of s. This model implicitly incorporates the transition probabilities by being weighted for each state by the number of times it is achieved from the current state. Over the number of iterations, this temporal difference learning converges similarly to the Bellman equations. Thank you.